cause things change, but the memories don't. You only need the light when it's running low. Only miss the sun when it starts to snow.
What is an embedded system? So an embedded system is a processing system that actually does a single or few very specific functions. Now, this can function as a standalone unit or as part of a larger system. Now, what is an example of a standalone embedded system? For example, aircon remote. So it does very specific functions like takes in a user input and it controls the aircon typically through IR. So another example of embedded system as part of a larger system is the BIOS in a computer. So BIOS of a computer is responsible for turning on the computer and loading the main operating systems that's inside. Yeah. So the next property of embedded system is that it's highly reliable. Now, it has to do a few things and do it really well. So they are usually used in places where things can go really wrong. Like for example, there's a loss of life of a very critical system failure. So one example of it is a car anti-lock braking system. So in the event that the car anti-lock braking system, it does the wrong thing, it can result in a loss of life, like a car accident. Yeah. So the next property of embedded system is that it usually operates in real time. So there is a very crucial distinction between real time and running something really quickly. In a usual workstation, like desktop computer, it runs really quickly, like it can clock up to 4 gigahertz or even more. But embedded system usually runs a lot slower, like within a range of few hundred megahertz. Sorry. Now, running really quickly doesn't mean that you guarantee an output within a certain time. So we can actually calculate the upper bound of execution time mathematically or otherwise, but we can't guarantee that a fast system is able to meet that time. So a real-time system, right, is able to meet that time under all conditions. And there is a distinction between real-time and just being really fast. But why is real-time important? So let's look at the example of car again, because it's a highly advanced machine and it has very interesting safety considerations. So let's look at the engine control unit. One of its functions is to actually fire the spark plug at the correct timing to ensure consistent combustion of the engine. Now, in order to do this, because of the speed the engine runs at, it needs to fire the spark plug with a resolution of a few microseconds, 1 or 2 microseconds. Now it has to look at the inputs that are coming in, so like crankshaft angle, fuel ratio, and things like that. Then it tries to look for the best time to actually fire a spark plug. They need to do this within microseconds all the time. Now, if there is a non-real-time system doing that, it can be really fast, but there might be edge cases where it stops firing at the correct time. At the best case scenario, your engine makes some weird noise, life moves on, and nothing else goes wrong. In the worst case, your engine blows itself to bits. So this is where the distinction between a real-time system and a really fast computer comes in. Now, let's look at the microcontroller. So now I'll be introducing a microcontroller, which goes in the heart of most embedded systems. Now, microcontroller, I've highlighted in red at the bottom right corner. So that tiny little IC or integrated circuit, there is a fully standalone processor. By fully standalone, I mean that it has its own non-volatile memory. flash memory right inside it, and there's a RAM inside as well.
Okay, so I think you're muted.
Oh. Oh, it's recording here also.
Yeah, that's okay. I think obvious and not recording, but I'm just thinking for people, I mean, someone might join and then they will hear nothing.
Right.
Just keep going.
All right, cool. All right. So now I'll be introducing a microcontroller. So what you're seeing here is the internal block diagram of a microcontroller. I've highlighted in blue at the top of the diagram where the CPU itself is. And notice how the flash and the RAM is actually beside it. Another thing to take note of is that the flash is actually particularly small. It's like 128 kilobytes. And the RAM is like only 20 kilobytes. So there's a limitation of having everything in a single IC that has to be really small. In the red, I've highlighted some of the I/O interfaces that it has. So it can actually interface with many devices, but you don't need an external I/O controller to handle all of these interfaces. Now, what are some of the key differences between a microcontroller and a standard processor? I went through some of the key differences, like being standalone. It can wake up really fast. It can actually sleep. It has very low power sleep. One of the main key differences I want to talk about today is its memory mapping. So a memory map is shown on the right side. So you can see it has a very flat memory map. So there's no paging as compared to an x64 system. So you can see that how everything in this memory map is all the peripherals, is mapped out in the memory in a very linear way. So let's have a look at USAT1. Not sure. Okay, then I'll move on later. Okay. Oh, on the left, you can actually see the peripheral, the register itself. So that's actually how you interface with different peripherals. So I'll be talking about registers. Okay, so I'll be talking about registers now. Okay. So register is one of the main ways you can interface with the peripherals inside. I think I should. Yeah. Did I miss out something? Yeah. So I'll be introducing registers. So registers are how you interface with the components within the microcontroller. Now the system memory, I'll be using an analogy to actually describe registers, and hopefully it'll be easier to understand that way. So we can actually represent system memory as houses within a community. So each house serves a very specific function. Like for example, let's have a look on the right side. From fourth item from the top.
Cause things change, but the memories don't. You only need the light when it's burning low. Only miss the sun when it starts to snow.
Address. So going by the same example of USAT1, USAT1 has an address of 40013800. So that is how we address that house. Now, each house has multiple banks of registers, which are basically switches that we turn on and off. So each switch, right, actually have an address offset. So in this case, we are moving on to a different example. So let's look at port A. Port A has an address of 40010800. And within this house, you want to turn on a specific switch. So you want to turn on the pin 9 of port A. So that is the GPIO PA09. So in this case, we can look at the output data register. Now, this register is the one that does the turning on and off of GPIO pins. So you want to go into this register, you want to turn on pin 9. So we have the address offset here, that's 0C. So now the whole step is you have to go to port A, and then we find the bank of switches at 0C. And then we look for switch number 9 from the right side. Then we turn it on. Then going by that, we can actually turn on GPIO. Now this analogy was actually, I first came across the analogy on this blog at the bottom. So I highly recommend you go and check it out because the author actually goes in huge details of how to actually program on a specific microcontroller called an MSP430. While it's a different architecture, the concept applies across most microcontrollers. Yeah. So now, practically, what does this mean? So here I've actually extracted some of the code from an existing project that I created. So note that this is actually a different microcontroller, STM32G430 rather than the previous one, which is an F103. Now, registers are actually usually predefined. So you can actually tell that I'm actually looking at this header file here. And inside this header file, it has a bunch of definitions already. So if you look at the bottom right, that's where the GPIO registers are defined. So it has an offset AHB2 peripheral base is a definition for 400000. So we add 0800 to it, and then there is actually GPIO-C. Because, okay, the reason why it's a different GPIO bank now is because it's a different microcontroller, so the addresses are different. Now, then at the top, oh, sorry, let's look at the bottom left first. So you can see that it's actually defined as a pointer to this particular GPIO address. And it's a shrub. So if you look at the top right, you can see that this is where the shrub is pointing to. So we can simply address it by going into the, let's look at the upper left side of the screen. So you can see that I can turn on pins by simply going to GPIO. X refers to the bank. So it can be A, B, C, D, or E, F, or G. And then I do that caret mark dereferencing thing. And then ODR is the register, that's output data register. Then I can simply set the 9th switch to 1, and that turns on that particular bank. So let's say I have a GPIO-C ODR, then I turn the 9th switch from the right on. That is GPIO-C09 that's being turned on. So that's how you can practically use registers. Now, to be even more practical, I don't usually address the register directly like this. I use this thing called HAL. That's a hardware abstraction layer. In short is HAL. Now, manufacturers usually provide drivers for different peripherals. You can use these peripherals. You can use this driver to actually do things with the peripherals without having to meddle with the registers itself. What this does is your code becomes portable, such that when I can switch out the hardware, but even though registers are different, I don't have to change my code because it's the driver itself that changes. Yeah. But there are some cases where you can't use the hardware abstraction layer. So like, for example, in a timer, in a hardware timer is actually very versatile. You can do things like PWM, you can do interrupts, you can time events. You can count the number of events. these are very specific functions which the manufacturer can't possibly think of all the permutation of what you want to do. So as a result, you're expected to write the register directly. All right, next, I'll be going through bare metal applications. So bare metal applications are applications where there is no operating systems involved. So on the right, you can actually see, it looks like a very basic C code. It just has a main function. And it just runs through everything. There's no OS involved. So this main code runs on the hardware directly. Now, this in a bare metal application is usually single threaded. Well, there are specific, like it doesn't apply all the time. Like there are some microcontrollers that have 2 cores or 3 cores, but we are looking at, but usually it's single threaded. Now, you're going to do multitasking. While it's single threaded, so you can't actually run 2 main code at the same time. So you actually have to handle multitasking through the use of state machines, through the use of event interrupt. So like for example, I'm running certain things, something else happens. So I interrupt this code and then do another set of things. And then once this finishes, returns execution to where it left off. And then you use timers to actually create to run things periodically. So let's say I want to water the plants every 5 minutes. So I will set out a timer that turns on the water every 5 minutes.
Isaac, could you share with me what you mean by event interrupt? So if I understand this correctly, you have the computer is executing line by line,
correct?
Right? And then how does another event come in to interrupt that execution? And how do you let it understand that another event has happened?
Okay, so this usually requires you to configure the peripherals itself. So like, for example, I have a UI. A UI is a communication protocol that talks to other devices. So let's say I have another device that sends data to my microcontroller. So my UI will trigger a receive interrupt. And then this interrupt will be handled by another separate block in the microcontroller. So it's not handled by the CPU. So it's called an interrupt controller. Its full name is Nested Vector Interrupt Controller, NVIC for short. So this interrupt controller will take over the execution temporarily, or rather, it tells the CPU to go to another part of the code. And the CPU immediately moves to that part of the code. It runs it, or then it finishes, and then it returns execution back to where it left off.
Okay.
Yeah. So actually, I can show you where the interrupt control actually happens. So let's have a look back at this block diagram here. So let's look at the blue block. We can see the largest block there is CPU. Right underneath it is the NVIC. That's the interrupt controller for short. So that is the purpose of it. Oops. All right. So next is I want to talk about super loop programming. So in a microcontroller, because it's running without an operating system, the code must not leave the main code. By main code, I mean this first line of this code block that I have here is int main void. Once it leaves this block, the CPU program counter will continue ticking. So it keep increasing and executing whatever is in the flash memory, which usually is not defined at all. So we don't know what the CPU state become undefined and it does unpredictable things, which can be quite catastrophic actually. So for super loop programming, it's happened between line 5 and line 11. So it's this while loop that continues running and it will never exit. So in a super loop programming, all this action from 1 to the nth action, whatever action you have, all these tasks, right, you run in sequence. So it runs 1, 2, 3, 4, and then once that's the last one, it returns back to 1. Now, it doesn't look very useful, but you can actually, through this, right, you can implement different things like state machines within this super loop, such that it does things when there are actually an event that triggers that state. Okay. Now I want to talk about real-time operating system, which is just now we talked about running without an operating system. Now we have an operating system. Now as microcontrollers actually get more powerful, we're able to run more lightweight real-time operating systems that can actually handle multitasking for us. Now, as mentioned earlier, real-time operating system actually need timing specification. In this case, we'll refer to this timing specification as deadlines. So a deadline can be categorized as hard deadline. That is when a system critically fails or loss of life occurs. For example, a car engine control unit or the anti-lock braking system that I gave earlier. Another example is an aircraft flight computer. Now, the opposite of hard deadline is soft deadline. A soft deadline is when a system can fail, but it can actually recover from this failure. So for example, an air conditioner, if it fails, it doesn't really matter. You can just catch that failure and then just reset the CPU. So another example is audio-visual system, which it can fail without any issues. Now, real-time system is highly deterministic. What this means is that the timing specification can be clearly defined through mathematically by actually sitting down and do static analysis of the code. We can determine it by doing experiments and see what is the worst case scenario. Now, it also means that it has very low jitter. So I put in an input, it returns an output within the same amount of time. Now, a real-time operating system functions similar to an actual operating system, except that it is lightweight. So in this case, you can actually run multiple tasks at the same time. So in this case, we break down the application code into smaller chunks. So here I show an example where there was like action 1, action 2, action 3, action 4. Now we can break them up into task 1, task 2, task 3. And each of them are running in parallel. And each of these tasks has its own context, meaning it does not share data with the other tasks. So by dividing this application code into smaller tasks, it actually makes the code cleaner, like a lot cleaner. So the use of real-time operating system is actually highly recommended for applications where you have a lot of things going on and your super loop gets really long and you have like nested state machines. So what I mean is I have a state machine, within that state machine, another state machine, and yet another state machine. That's when you know you should start using a real-time operating system. Now, a real-time operating system actually comes in 2 different flavors. First one is event-driven real-time operating system. It's also known as preemptive. So the OS actually switches the context to a task with the highest priority. So let's say I have a low priority task that's just doing simple things. Then I have a higher priority task. Let's say user comes in and then requests for an input. And then the OS will immediately switch to that task that has a higher priority. And then it runs that task. And once it's done, it switches back to what it was doing before. A time slice Rtos shares the time evenly by switching a task consistently. So let's say it switches a task every 10 milliseconds. So each task will get a very fair and even share of CPU time. I want to take a look at Rtos. Rtos is one of the most popular Rtos that is like out there. It's also widely supported by manufacturers, mostly because it's been around for very long. It's open source. So what this means practically for programmers is that it has a lot of people that actually look into it and is guaranteed to work. It has a preemptive kernel, although you can have the option to change it, but it's usually not supported because it's not a function that they expect people to use. Now, memory can be dynamically allocated during runtime or statically allocated during compile time. Now, Rtos has a bunch of tools to help you write your code easier and to help you to do things like flow control, do communication between different tasks. So as I mentioned earlier, each task runs in its own context. So that means that it doesn't share any data. So we need to have some form of communication between them so that you can actually share data across them. So it does this by having things like task notification, queues, stream message buffers, and then for resource guarding. So like, for example, I have two threads that want to use a single peripheral. I need a way to guard this peripheral such that the two tasks doesn't use them at the same time, which can have quite some disastrous result. For example, when I'm sending data out over UART, so I'm sending a data. A wants to send this amount of data. B wants to send the same amount of data. But when I'm sending halfway through, A is sending, suddenly the OS switches to task B and then immediately uses the peripheral. So it starts sending B. But this is wrong because I want to have this full continuous block. Now I have A and then B and then A again because of the task switching. So resource guarding prevents that from happening by preventing task B from using a peripheral until task A has finished using it.
So in practice, is a task one function, or can a task consist of many functions? And also, does each task run in its own thread, or can one thread run many tasks?
A task is a thread by itself. So it's usually broken. So I have an application. I usually, in Rtos, I'll try to break it down into smaller portions. So each of these smaller portions is a single thread. And each of these threads, it runs in its own context, and it's actually running parallel with other threads. So the way the CPU ensures that every thread gets its own share of CPU time is by doing context switching. And context switching can happen anytime during a code execution, as long as a task becomes ready for execution. So for flow control, usually I'll have some kind of blocking system, which I'll explain later. Actually, why not I go ahead and, where is it? Okay, yeah. So here I actually have an example of a blocking action. So let's look at the code block on the left side. So we have a look at task 2 and task 3. Task 3 is running from sub action 1, and then it goes into this task notification tick. So what it's doing here is waiting for a notification to actually continue running. So over here, it waits here forever. Then at the same time, I have task 2 that's running action 1. Is the cursor showing? Oh, yes, it's okay. So I have sub action 1 and sub action 2. So once you finish these two actions, it goes into this task notification GIF, which tells task 3 that, hey, wake up and continue running. So that's where it goes on to sub action 2, and then it does a delay here, and then it goes back to sub action 1, and then it waits again. So at this time, right, when it's blocking, the CPU will switch context over to task 2, and then it iterates again. So action 1, action 2, task give, and then this action wakes, this task wake up, does action 2. So usually the the event that actually wakes up, the task that actually wakes up, the first one that wakes up, then execute is the one with the higher priority. So OS will always give, you will look through the list of tasks that is really run, and you will take the highest priority one and always run that one. So because of this, right, the program should take care of prevent situation where the highest priority task actually runs forever, and then it deprives all other tasks of their CPU time. So this is where flow control comes in very handy. So you have to do a blocking action, or you can put a delay here to actually ensure that the other function has time to run. So at the same time, as I mentioned earlier, the programmer has to take care of resource sharing that will prevent conditions like deadlock or race condition where both functions are actually using the same variable. And yeah, okay, there's quite a lot of details actually, so I won't be going through that much. Yeah, okay. So talking about RTOS, so when do we use Rtos? You use it when your code starts looking like this, where it becomes really messy. I'm half joking because nobody code looks like that, and I actually no idea what language this is. Yeah. So RTOS helps you clean up your code because it breaks your application down into smaller functions. So it helps to prevent situation where your code becomes unreadable, basically. So next, I want to talk about embedded Linux, which is becoming very popular. So Linux has some specific hardware requirements that might prevent it from running on microcontrollers. There are open source projects that runs Linux on a standard microcontroller like the one that I showed earlier, but that usually comes with a lot of issues like, because it's not supported by Linux, basically. Now, what advantages does embedded Linux actually bring? So Linux actually helps to extract away the hardware, and you can use very low level, it extracts away the hardware and the low level protocols that it's actually doing. So like, for example, I have a fully featured network stack. So I can actually open HTTP server, I can open all kinds of, so I can communicate to a cloud service, for example. And then it also allows you to use high-level language like Python, Rust. So what this means that your code is very portable. So this same Python script or Rust code that I actually compile, right, I can actually run it on another hardware as long as it's running embedded Linux. Now it has a very powerful kernel which allows you to do seamless multitasking. So it takes away a lot of considerations that the programmer has to think about. So for that, I can run like 5 different Python scripts all at the same time. And it looks from the outside, it's almost like all of them running at the same time, but in actual fact, at one single point in time, only one script is running at one time because it has only like one CPU. Okay, so this one is not really an advantage, it's more a disadvantage because embedded Linux has a very large and bulky kernel. It's very difficult to achieve real-time performance, especially when you use very high-level languages like Python. So it actually requires a lot more thought into the programming. And usually you have to use very low-level languages to actually achieve real-time performance on Linux. Now, speaking of embedded Linux, why don't we also introduce some microcontroller and microprocessor hybrid. We call them system on chip because is a full system with multiple different elements, like you have a microprocessor and a microcontroller here. So in the block diagram on the right side, on the top left, this is a microprocessor. So you can see that it doesn't actually have a flash memory. I mean, there is some ROMs here, but it's usually not enough for you to run things. So you have to have like actual memory on the outside. So where is it actually found in? You can see there is a few. Okay, I think it's a bit hard to read, but over here where I'm pointing, it says LPDDR3. So that's for the RAM system. So this is specifically for the microprocessor. On the other hand, over here, I have the microcontroller over here. So what does this actually do? Because they're on the same die, it's very, very convenient for designer to actually implement in hardware. So this allows a designer to actually run high performance applications on the microprocessor here. And then while still retaining the real-time nature of a microcontroller by delegating some of the, for example, like control, like signaling and controls to the microcontroller here. So some of the application of this includes AI, where usually you have some form of Linux system running here, and it's doing all the very fast computation, while at the same time still handling the low-level signaling here. Another application is computer vision. Natural language processing is a fancy word for speech recognition, yes. Okay, so, oops. Okay, so this type of systems, right, are usually reserved for applications where low power is not a requirement because it runs really fast. It takes a lot of power. So these can be commonly found in very high-end, high-performance IoT devices that requires the use of like where you can actually plug into like actual power and it's not battery power basically. Okay. So as now you probably already guessed, there's quite the lines between what is a microcontroller, what is a microprocessor, what is embedded, and what is not really embedded. It's actually quite blurred already. So you have new devices coming out over the last couple of years. You have things like multi-core microcontrollers. So you have a microcontroller that has like 2 cores. One example is an RP2040. There's a new microcontroller from Raspberry Pi Foundation. It features a dual-core M3 microcontroller, I believe. And then microcontrollers with AI accelerators on board. So what this means that you don't even need the microprocessor anymore. You just run everything in the AI accelerator. Then you have microcontrollers graphic processors. So you can run graphic applications that can power an entire screen just from a microcontroller, which wasn't possible like maybe 10 years ago. You have an FPGA microcontroller hybrid, and you have a microcontroller and RF transceiver hybrid. So people are starting to put things together that wasn't available before. And these such integrations of like different things inside enables you to make very high performance and really compact designs. So because they're actually very specialized, I won't be going through some of these things because it's a very deep topic, basically. So I want to show you some of the tools that I actually use. So one of the most common development kits available is STM Nucleo. So that's this huge light blue thing over here. And then AT-SAM is also another popular microcontroller. So that's this dark blue one here. Personally, I like to use the J-Link for my projects because this is a universal programmer and it supports all kinds of devices. I'm using the J-Link Mini Edu. Oh, yeah. It's actually used for, it's designed for educational use basically, and it's really cheap. But it has to be education. You can't use it for commercial applications. So for a research project, it's a really good tool because it can target all kinds of microcontrollers. Allows you to experiment with more things. So in the industry, people usually use very like manufacturer tools, like for example, this middle one, that is from ST Micro. So it targets the STM32. So that's the ST-Link. Then from Microchip, you have the Pink Kit 4, which targets AT-SAM, which is also from Microchip. Now I like to demo some of the tools. So over here, I have a board. Oops. So this is a simple distance sensor demo. So over here, I have a ultrasonic sensor. So it communicates with the microcontroller here over I2C. So I will just quickly show. Okay. So here is what the software is going to look like. So I originally planned for this to be a demo of like a fake door open and closing system. So hence the distance sensor. Here are some references to opening and closing doors. So what this demonstrates? It demonstrates a super loop programming. So you have a start, it reads a sonar, detects a distance, and then it opens things, close, and then once it finishes execution, it doesn't end here, it actually goes back to the start. So it reads again. So you can see that if, for example, there's no event happening, it just keeps reading until something happens and it moves on. Then that's it, super loop programming. So I'll also be quickly showing how to actually configure peripherals, but rather than looking into registers, we will be using code generators. All right. So here is some of the tools involved in this demo. So I'm currently using a Nucleo 32 board. So that's this tiny blue color thing over here. I have a distance sensor. Software-wise, I'm using the ID that ST Micro meets. So that is it's an ID that's based on Eclipse, and then they package in their code generator directly in as a plugin. So for debugger, usually you will have a separate debugger, but this dev kit comes with its own debugger. Yeah, so I do not need one. I'll also be showing how to use a logic analyzer to debug hardware issues, like specifically in the communication line. Okay. So here's the price involved actually. The price is actually quite cheap. So for the microcontroller, I'm using a dev kit, which we are looking at 12 USD from Mouser. But if you get the bare IC and you design your own board, it's about $6. It used to be cheaper before the chip shortage actually. For distance sensor, I'm using one that communicates using I2C, which makes things very convenient. But there are very cheap variants from AliExpress, like $2. For debugger, this $9 debugger is actually the STM32, ST-Link, sorry. So that's the one over here. This is $9. And then logic analyzer, this particular one I have is $15 from AliExpress. Oops, all right. So I'll just quickly show you the code generation. So let me switch my screen over to here. So I actually prepared the code before actually coming. So I also wrote the drivers that's on the right side. So you can see that it's actually I2C, so it has an address. For code generation, there is a very convenient, probably a very convenient tool to actually generate. So I'll just all right. Let me merge this in. All right. So this is the microcontroller. So it actually shows you the pins that is available for you to use. So for configuration, I actually pre-configured the project before the workshop so that I know that it definitely works. So we're actually using I2C, so that's where I have I2C. So you just come here, turn I2C on. We tell it how fast you want to talk to the device. And you don't usually have to touch many things actually. There's not many things to touch. So as you can see, this is the event interrupts. So for example, I can trigger an interrupt to wake the PC up, wake the CPU up, or do some specific set of actions whenever I finish my I2C transfer. So if I want to do that, I can just turn this on. Yeah. So that's about it. Then for I/O pins, previously we actually looked at the register directly, turning it on from them, but we actually don't have to. So to actually turn on the I/O pin, so I have configured this. It actually pre-configured as LD2. So you can see here it says GPIO output. Now I've already pre-generated the things, so I don't have to generate, but you can save it and you'll ask you whether you want to generate the code. All right, so once you finish generating, you get a full project with all the files inside. You have a main code, so this is where you put your things. So here you can see some of the code that I've already written. So initialize the system, initialize your I/O, this UART connection. You'll see how it comes to play later. Yeah. So you can look at there's I2C here also. Then you have then this is where I send a statement just so that I know that it's actually working. Right now, so let's have a look at how I'm configuring a sensor that's through I2C. So over here, by using the hardware abstraction layer, you can see that everything is done in a single line. So if I actually open this up, it's actually very complicated if I don't use a hardware abstraction layer. So you can see it actually sets the state. It puts the data in here, and then it does transfer and all that things here. So by using a hardware abstraction layer, I can use a single statement to do everything. And the best part about this is this code works almost anywhere as long as it's STM32, because all these lower level code changes, but it doesn't concern the programmer. Okay, so I will connect this up and show how it works.
This will appear and then you can.
Oh yeah, sure. You can move this all the way down.
Do you still show the code?
Sorry?
Do you still need to show this code or can you switch to showing that?
Can we have this in the screen instead? In the camera instead? Yes, because I can still show the code. Oh, oops. Oh, that's
I'm gonna chop out this part.
yeah, sure.
Yeah. Now see. I'm gonna make this a little bigger. Your code still won't be covered, right?
Yeah, it's okay. I'll be using that top.
And then I should focus on this.
Yeah. All right. Okay, so in order to flash the code in, I simply just hit run over here and then it flashes the code in. Oh, oops. Okay, it's flashing now. So it's building the file and then now it's connecting a debugger and it's done. So now let's have a look at LD2, which is this LVD over here. So when I move it up, okay, oops. Okay, this thing can it show up? No, okay, it doesn't show up on camera. Okay, I will. I'll be showing you another screen. So this screen, so what it is showing is the execution state of my code. As you can see, it's actually currently looking at the distance that the sensor is measuring. So I put my hand over, the distance actually lowered, and then it shows doors closed. Sorry. So once I move it away, so it shows door open. Then once I move it away, it shows door closed. So that is just a very quick demo of using the tools. Now, I'll be talking more about debugging code now. So usually debugging, the most common way debugging is to use, oh yeah, I think I can move it away. Some of the most common way to debug is actually use printf statements, but printf statement doesn't tell you the internal state of the code execution. So here I want to show you the use of an actual debugger. So I will start debugging. So here I'm in debugger view. So I can see exactly what the CPU is doing exactly without just spamming printf statements everywhere. So let's say I can step into a specific function and I can see that now what is it doing? It's actually trying to initialize something. Then I'll step out of it. I'll put a breakpoint here. So I'll let it run to the breakpoint. I'll enter this function. So now I can see that I'm actually trying to send out something now. So let me step here, step inside. Then you can see now I'm actually Now I'm actually inside. I can see exactly what is it doing. So like over here, I can see the internal variables. So that is the use of debugger. Now, use of debugger is highly recommended for large programs because you can see the states of execution. You can actually have all these views. Okay, then next I want to show the logic analyzer. So this is used to kind of like you sniff the, can you see sniff the communication buses? So you can actually, it helps you to see what message is being sent, even though your code may not actually respond to the things that you are sending. So you produce wrong results sometimes. So I'll just connect this over here. Okay. Right. Okay, let me switch my screen over to a new. All right. Oops. All right, so I've connected to my device. So I will change the marker. So I'll be sniffing on the 2 lines on my communication bus. All right, so you can see all these are the packets that are actually being sent by my microcontroller. So how do you actually, you can't possibly read this, but the logic analyzer has decoders for protocols. So I'll just turn on I2C decoder. So now I need to tell you which bus is the clock and which is the data line. So I'll just put it like that. And then here we can actually look at very specifically what is being sent by my microcontroller. So you can see that firstly it addresses the device, then it writes 02, and it executes a read. Now this is actually a separate topic that is on I2C communication, so we won't be going through this as well. So this is actually the tools that are actually used for debugging. All right. So now I'll move back to my, so now I'll be moving back to the, continue the presentation. So let me turn this off. And let me turn, oops. All right. Oh, let me move these back, right? Okay, so we have come to the conclusion of this very short workshop on embedded systems. So this is really what we talk about for today is actually the CPU architecture of a microcontroller and the programming principles, like how do you actually program it? How do you talk to different peripherals? How do you actually do multitasking and flow control? So what is next if you are really interested, you want to go into embedded system? I highly recommend looking into communication protocols. So one of some most common communication protocol is UART, I2C, and SPI. CAN bus is something that's becoming more common, especially for high reliability system, because it was originally designed for use in cars. So embedded system also involves a lot of different disciplines. So one very important thing to actually keep in mind is how do you design digital systems? So like, how do you use logic gates? How do you actually interface between different ICs? Another thing to look into is also analog design. So embedded system usually combine digital and analog domain at the same time. So in a microcontroller, usually you have analog digital converters that takes in analog inputs. They can do processing on the analog input and then output it through a digital and analog converter. So that actually concludes the end of my short sharing. So yeah.
Okay, nice. Actually, I'm gonna take it back to the ground. Okay.
All right.
Okay, I'll make a conclusion.
Okay.
So you can mute yourself. So that was Isaac Wong from NTU Singapore. Thank you very much, Isaac, for the presentation. This was very, very all the major things were mentioned, so it was very, very useful for someone wanting to start out, right? We don't pretend that this will be everything you need for you to start, for you to actually build a system, but what Isaac has offered us is the key set of key components that you would want to have on hand for you to actually start programming. And then there are many other YouTube tutorials and other tutorials online that you can then, to delve deeply in the concepts that is touched on, you can do that on your own, right? But all the key things that are needed, he has mentioned. So that's the goal with these sessions, where we just demonstrate to you listeners that the tools that people are using in advanced economies like Singapore here, those tools, you too have them at hand. And as Isaac has showed today, these are $9 things, the $7 things. These are not extremely expensive things. These are things that with a little bit of will and desire to program, you can program a robot, you can program an engine control unit, you can do a lot of things with embedded programming. It is a very powerful form of programming, which perhaps very few have heard of. So we hope that with this session, we have given you a useful enough introduction to embedded programming. Thank you, and thank you, Isaac.
Thank you.
Cause things change, but the memories don't. You only need the light when it's burning low.